Next, we'll talk about logarithms. A logarithm with base b is defined to be the compositional inverse function of the exponential function with base b, which is what we just talked about in the last video. So, for example, if you have y is equal to 2 to the x, 2 to the x here is an exponential function of x. This can be rewritten in terms of the inverse function as saying that log base 2 of y will get us back to x. So remember that the inverse function interchanges the roles of x and y. So saying that y is equal to 2 to the x is the same thing as saying that log base 2 of y is equal to x. And these two equations are equivalent to each other. We usually call the left equation the exponential form of the equation because it involves an exponential. And then we will call the right side the logarithmic form just because it involves this logarithmic function. But the point is that a logarithm is defined to be the inverse function to its corresponding exponential function. So for every base, you'll have a corresponding logarithm with that base. So this would be called log base 2. And because these are inverse functions, they cancel when composed. So for example, if I let my function f of x equal 2 to the x, like we have up above, then what I'm saying is that its compositional inverse is given by this logarithm. And remember what that means in practice is that if you plug one of these into the other, then in some sense they cancel out and leave you with your original input x. So for example, if I take log base 2 and as its input, I plug in its inverse function, like that, then these things will cancel and I'll be left with just x. And the same thing works whenever I compose in the other order. So if I have my function 2 to the x, and as my input I use its inverse function, log base 2 of x, notice that this log base 2 of x is in the exponent up here. So this is an exponent. But these again will cancel, and I'll be left with just x. So this is called the inverse property. Oops. Sorry, that got a little messy. All that it's saying is that if you plug one of these functions into the other, then in some sense they're cancellative. And if you'd like, you can write this sort of cancellation symbol to say that I'm composing these two inverse functions and therefore they'll cancel out to just give me x. That's fine with me, but just remember that what we're doing is composing two inverse functions. This is not like a cancellation of 1/3 times 3, for example, right? So this is a little bit different than a multiplicative or additive cancellation. This is just saying that because I've composed two inverse functions, they'll cancel each other out. So we can use this cancellation property to convert from one of these forms to the other. So up at the top here, you see this exponential form of the equation and the corresponding logarithmic form. So we can use this inverse property to get one or the other of these forms. And notice that these forms can be useful in different contexts because here in the exponential form, I've isolated y, but in the logarithmic form, I've isolated x. So it may be useful to transfer from one of these to the other, depending on what it is that you're trying to get at or what expression you want to isolate. So just to give you sort of an example of that, where you might want to isolate something specific, if I tell you that y is equal to x cubed, then maybe I might want to solve for x here. So what I would do in order to solve for x is I would probably apply a cube root to both sides. So I would say that the cube root of the left side is equal to the cube root of the right side. But these operations, the cube root and the cube, those are inverse functions, and therefore these things will cancel out and I'll be left with just x on the right side. So now I've changed from the cube root form, from the cubic form of the equation to the cube root form of the equation, and that allows me to isolate these different variables. So we can do the same thing with this exponential form of the equation. So let's say that I wanted to get x by itself here. what I could do is, just like I did above, I could apply the appropriate inverse function here. So notice that in this top example, I'm not dividing by 3 or dividing by a cube root or anything like that. I'm just applying the appropriate inverse function to both sides in order to cancel out whatever I want. In this case, I wanted to cancel a cube, and to do that, I would apply the inverse function, which is the cube root. So similarly here, if I wanted to get this x by itself, I could apply the appropriate inverse function to this right side. Now, the inverse of 2 to the x would be log base 2 of x. And just like I did above, I want to apply that to both sides. So if I apply log base 2 to both sides, then that says that log base 2 of the left side is equal to log base 2 of the right side. But now notice on the right side, I've composed inverse functions. So I have log base 2, which was defined to be the inverse function of 2 to the x. So on this side, those things would cancel, and I would just be left with x. So therefore, we get the logarithmic form of the equation like I had above. So now we've gone from the exponential form to the log form. So I've gone from having y isolated to having x isolated. We can go back in the other direction if we'd like to. So if I have an equation that looks like this, and I want to transform it into its corresponding exponential form, then what I would need to do is I would need to apply the appropriate inverse function to both sides. Now, if I want to kill a log base 2, then I should apply its inverse function, which is exponentiation with base 2. So I should exponentiate on both sides with the base 2. So that says that 2 to the left side is equal to 2 to the right side. So here I'm again applying the appropriate inverse function to both sides, but notice that on the left side I have a composition of inverse functions. So those things cancel out, and I'm left with just y is equal to 2 to the x, and we've gotten back to the exponential form. So that allows us to transfer back and forth between the two forms if we'd like to. You can just apply the appropriate inverse function to get back and forth between them. And we're actually going to use this to evaluate certain expressions. So the point is that if you want to evaluate a logarithm, let's say you have log base b of b to the x, we know that this is a composition of inverse functions, and therefore these things will cancel out to just give you your original input x. And we can use this rule to evaluate certain logarithms. So for example, if I wanted to compute something like log base 2 of 8, well, it's a little bit hard to see immediately what this would be, but we know that if I have log base 2 of 2 to the something, then that log base 2 and that exponential base of 2, those things can cancel out. So what I'd like to do is I'd like to rewrite the inside as a power of 2. So I could rewrite that 8 as a 2 cubed. But we know that log base 2 of 2 to the x would just be x. And the same thing works here for a concrete exponent 3. So here I have a log base 2 of 2 cubed. These things are still going to cancel to give me 3. So we can apply this for any value of x. Anytime you have a log base 2 of 2 to the something, then those inverse functions will cancel out and you'll just get that something, the exponent on the 2. So let me show you another example here. Let's say that you have log base 2 of 1/2. Again, what I'd like to do is I'd like to use this inverse property up at the top. So I want to rewrite the inside here as a power of 2. And thankfully I can. So I have that this is log base 2 of, the way that I would write 1/2 as a power of 2 is 2 to the negative first power. But again, because now I'm composing these inverse functions, those things will cancel and I'll be left with just a -1. So we can evaluate these logarithms concretely as long as the inside is a power of the appropriate base. So in this case, I'm working with log base 2. That means in order to cancel, I want the inside to be a power of 2. And then I can just cancel. So let's look at another one here. So let's say that you have log base 2 of 1. Now, how can I write 1 as a power of 2? It would be 2 to the 0th power. And now I have log base 2 of 2 to the something. I know that these things cancel out, so I would just be left with that exponent, which is 0. Now, there's something that I want to point out here, an interpretation of the logarithm that might help you whenever you're evaluating these. So notice the relationship between the base, the input here, and this exponent sitting outside. So notice that this first term can be thought of as asking, what exponent would I put on a 2 in order to get an 8? So what exponent would you put on a 2 to get an 8? Well, you would put a 3 as your exponent in order to get an 8. So this is the exponential form of this logarithmic form. So you can use that to your advantage. You can think of this logarithm as just asking, what exponent would I put on a 2 to get this number? So for example, in B, it's asking, what exponent would you put on a 2 to get a 1/2? The exponent that you would put on a 2 to get a 1/2 is a -1. In other words, 2 to the -1st power is a 1/2. And similarly here, what exponent would you put on a 2 to get a 1? The exponent you would put on a 2 to get a 1 would be a 0, because 2 to the 0 is 1. So you can use that reading of this logarithm to your advantage. That won't always work. For example, if you have log base 2 of 7, we don't know what exponent you would put on a 2 to get a 7. That's going to be some complicated decimal answer. So here you would just use a calculator. In other words, whenever you're trying to evaluate log base 2 of something, we really need that inside to be a simple power of this base, like it was in A, B, and C. There's some special logarithms that we're going to look at. But the analysis for these is similar to the analysis that we have in the example that I just wrote up. The only difference here is that we might abbreviate log base e and log base 10. So every logarithm has a base, because that logarithm is the inverse function of the exponential function with that base. So if f is equal to e to the x, then f inverse would be log base e of x. But we normally abbreviate log base e of x as the natural logarithm of x. So if you see ln of x, that's defined to be the inverse function of e to the x. So you could write it this way, but ordinarily we would just write it as ln of x. And similarly here, if you want the inverse function of 10 to the x, that one's so commonly used that we would abbreviate its inverse function, which is log base 10 of x, as just ordinary log of x. So if you don't see an explicit base here, then implicitly the base is 10 for a logarithm, and the base for the natural logarithm is the base e. So every logarithm has a base, but in these two cases, we're not going to actually write the base. ln is the inverse of e to the x, and log of x is the inverse of 10 to the x. So these are some shorthands that we might use. If you don't want to use the shorthand, it's okay with me if you write them this way. But ordinarily, we wouldn't write log base e, we would just write the natural logarithm. So you'll explore some of these things that I've talked about in more detail in the examples, but there's one last thing that occurs in this section, which is graphing logarithms. So I want to talk about that shortly. There are two ways that you can graph logarithms. One is by thinking of them as an inverse function. So for example, if I wanted to graph this function, f of x is equal to ln of x. One option would be to do something like this. So we saw in the last section that e to the x has a picture that looks like this. And we also know that e to the x is the inverse function of ln of x. So we saw in the last section that it always goes through the point 0, 1, because e to the 0 is 1. And we also know that if you have inverse functions, then those inverse functions have graphs which are reflected across this line y equals x from each other, because an inverse function just interchanges the roles of x and y. So if you take this function e to the x and you flip it across this line, so you take its reflection across y equals x, then you'll get the graph of its inverse function. Its inverse function here is going to now go through 1, 0, because we flipped the x, y's for the original function, and this would be a graph of ln of x. So that's one way to obtain the graph of a logarithm. You just know the graph of the original exponential, and then you flip it across y equals x to get the graph of the inverse function. Now notice that for this logarithm, because it's the inverse to e to the x, it will have the opposite domain and range behavior of e to the x. So in this case, the domain of a logarithm is only positive numbers, because that was the range of the exponential. And similarly, the range of the logarithm is going to be all real numbers, because that was the domain of the exponential. So the inverse function is going to have the flipped domain and range from the original function. So this is the domain and range for any logarithm. In particular, notice that the inside of a logarithm has to be a positive number. That's the main takeaway that I want you to have from this. So the graph of the logarithm is only defined for positive x values. It has this vertical asymptote at x equals 0, and you can't graph the logarithm to the left of this vertical bar, because a logarithm is only defined for these positive values. So that's one way to graph a logarithm. The second way that you have to graph a logarithm is using this plug-in method that we've been talking about. This works generally for graphing anything, as long as you're able to plug in some values. So this is just plugging in. Let's say that you want to graph the function f of x is equal to log base 2 of x. Then what we can do is we can try plugging in a few specific values. So for example, if I plug in a 1 into this function, then this would be log base 2 of 1. Remember, this is asking what exponent would I put on a 2 to get a 1. So the exponent that I would put on a 2 to get a 1 would be 0. 2 to the 0 is 1. So the output here would be 0, and that means we're going through this point. In other words, 1, 0 is a point that lives on this graph. Similarly, maybe I could plug in an x value of 1/2. If I plug in 1/2 as my x value, then my output would be log base 2 of 1/2. That's saying what exponent would I put on a 2 to get a 1/2? I would put a -1 exponent on a 2 to get a 1/2. So that would live down here at -1 as its output value. Similarly, if I plug in a 2, then what I would get is log base 2 of 2. What exponent would you put on a 2 to get a 2? I would just put a 1 as my exponent. 2 to the 1 is 2. So that gives me this point up here. And maybe let's do one more. So let's say that I have log base 2 of 4. If you want to pause the video for a second and think about this one yourself, then you can. But the question is, what exponent would I put on a 2 in order to get a 4? And the answer is that you would put the exponent 2 on a 2 to get a 4. In other words, you would have 2 squared equals 4. So the exponent that we're looking for is a 2. So if I come over here to the point 4, then I know that the corresponding y value would be 2. And in general, if I could plug in a bunch of points, then what I would get is this general shape. Whoops. We're going to have a vertical asymptote here at x equals 0. And the logarithm is going to go like that. So those are two methods for graphing logarithms.